I'm pleased to announce that we have Marek Kirs leading his presentation. Marek is a microbiologist at the Water Resources Research Center. His research focuses on microbial water quality and public health issues. He received his BSc from Tartu University in Estonia, MSc from the University of Edinburgh in UK, and PhD from the University of Rhode Island. He completed his postdoctoral trainings at the University of North Carolina at Chapel Hill, and he also has been a proud recipient of Fulbright and British Council scholarships. So, again, please welcome Dr. Marek Kirs. Thank you.
Thank you. Okay. So that was pretty much the introduction. So first I start with stuff that you can Google. So why the water quality matters? If I go to stakeholder meetings, people talk usually about water quantity, but water quality usually seems to be ignored and being on the background. So I think it matters because there is a human health concern, and so drinking water, recreational water, seafood, they can all be the importance for humans. And there is also environmental concern because habitat degradation from sewage input to the environment. And I think these two things have been overlooked, but that they're connected is overlooked. But I think it's extremely important to consider. I'm not going so much to talk about it because that's one of my interests, but I still don't have data really to talk about on this matter. So how clean our beaches? So this is from 2014 report. That's you can Google again. It's 10% of samples that were collected in the US. They exceed the recommended water quality standards. It is EPA estimates that roughly 3.5 million people become sick from sewage contamination related contact from sewage every year. It's estimated that it's cost like $35 per day if the person doesn't go to the beach. And Orange County is the often quoted fact that it's estimated that it lost every year 51 million from beach notifications to others. So next one, how clean our beaches? This is also not a one from Google. And in our history report, I was looking for a report that didn't read Google. That would be embarrassing. So how I ranked number 7, and it has been ranked like that our long time, I think at least a couple of years. And from out of 30 coastal states. I think we should rank better because I didn't count NRVC if I'm wrong, but you can check me. You can correct me if I'm wrong. I think NRVC reports the state are only based on the enterobacter measurements. So, and we all know that we have issues with the growth of enterobacter in the environment. So our background levels are much higher from the levels that we will see in North Carolina or in Rhode Island or in New Zealand, at least based on my experience. So what they reported was that we have quite a bit of number of beaches that are not actually monitored all the time, 415 beaches, and we have a few beaches that actually have some problems. And here are the over the time from 2009 to 2013, how big percent of samples from every year have been exceeding the beach advisory levels. I think it's based on. I don't think it is. I think that it is based on the enterobacter levels, these estimates. And remember the 4% for 2013 because I'm coming back to that. And 2013, that's based on beach action level that is based on the 60 enterobacter per 100 mil. So how do we know that water is coming? It's very simple. We measure for enterobacter and which record it. I'm very sorry if this is too simplified, but it's just an introduction. So it depends from the state what any state measures. California has 5 standards. We have 2. Our standards are based on enterobacter and cicatrine. So this MEI plate is blue columns being enterobacter, which are gram-positive facultative anaerobe. So they can grow equally well in incubator or in your gut. in anaerobic organisms. So they do both very well. And zipper prevalence is obligate anaerobic, so you can grow it only without oxygen. So it shouldn't replicate in the environment. So notifications, measurements, notifications are posted in Hawaii if any levels exceed 130 colony-forming units, and zipper prevalence 50 colony-forming units per 100 milliliter. And this is for both marine and freshwater. And it's just to comply with Hawaii, with new recreational water quality criteria. So I'm going to talk today about beach notifications, not about reporting. So methods are calculation-based and simple, so they're easy to perform. And these are supposedly indicators of sewage contamination and do not indicate risk from environmental pathogens such as Vibrios and Leptospira. And these are proxy organisms are used as there are too many pathogens, and concentrations of pathogens are usually too low to easily measure. And methods for pathogens are usually complicated as well. Issues. So these are there are three major issues that I'm going to cover today. These are the three ones. Current methods are too slow. I'm going to talk about rapid methods. There is no information on contamination source, and the samples that we collect are usually quite small, usually 100 milliliters. So we need bigger samples to really cover, for example, source-specific markers for pathogens. And I'm talking about the environmental impact that sewage when it enters to the environment, but how it actually impacts the environment and how this will feed back to our health. But that's if I have time. So current situation. So I got permission to show the slide from Dr. Griffin because I think it really shows what the rapid methods are about. So if you go to California, you'll see quite similar signs posted here. You see a sign like that. So that you should not swim, which actually means that the ocean water quality was good yesterday, and you should have not swum, and water quality might be okay today, but check out it tomorrow. So that's the idea. But yeah, anyway, so it looks very good. So EPA came up with these water quality, with new rapid methods for beach notification. So method 1611 came out 2012, and I think 1609 came out early last year, maybe not. So there are two methods. The 609 is a newer one and more advanced, more better method. And so the state can use beach action values to actually to notify beach stewards about possible dangers. So this is based on 75% from distribution from this industry. And notifications in Hawaii, as I said, are based on these values because this is completely voluntary. This is not the values that you're supposed to use. You can link it to the standard threshold, but standard threshold value that is 135 points. So that's the standard we're currently using. So this has been applied in California. So they have a lot of money and they can understand why they're doing it. So you can come to the beach and you can actually see that the water was collected in the morning and the results are posted immediately on the pizzeria next to the beach. So pros, you can same day response, improve service to visitors and residents. You can show that looks good for visitors. But cons, methods are complicated. Many states have beaches which are far away and hard to reach. Many beaches with very few visitors. It's cost, and after all, therefore, enterogoky. Why are we worried about enterogoky? It's Hawaii. And so, a couple of things. Methods complicated, that shouldn't be excused. They can be learned. Many beaches in Hawaii, we have many beaches in Hawaii. Many beaches are far away, yes, true, but in Hawaii it's quite small. So here we can collect samples quite fast. That's not true for Waikiki or Ala Moana. So I think this is not a technology that use every beach. That you would use on the populated beach, which is important for you. Cost is definitely an issue, and I cannot see that Clean Water Branch should sample Waikiki every day. I think the cost needs to be discussed and should be covered probably. I think by the hotels, maybe I'm naive, but that's my thought is. And then it's problem with enterovoc. And the problem with enterovoc remains, and I will talk about that. So limited testing in Hawaii. I did talk with, I think, Robin Hoshiro from EPA, and he said that 2 samples they have tested so far from Hawaii. And as I said, growth of enterovoc in the environment, if you're feeling that there is need for different tests to supplement that enterovoc-based test if you want to do the rapid test in Hawaii. At least I think. So the study that we did. So now we get to something to come over. So we collected 1 year of data around the island from 12 beaches, from these 12 subspecies names. And because the beaches were clean, we needed to also include 3 sites from the Alawai Canal, just to have high enterovoc counts and have a good comparison between the 3 different methods. We measured the levels of enterovoc by MEI, by enterolab, and by new methods 1611, because 1609 wasn't yet out. And so that's what we saw. So that was, if you take these samples and throw away samples that you had below the dictionaries or which are inhibited, which I'm coming shortly, we saw pretty good correlation between the 3 different methods tested. So this is the R square. The new DSM that was recently published by EPA says that if this is more than 0.6, you can use the alternative method. So it indicates that the new method can be used because it produces good correlation between all the 3 methods. So there is a good correlation. Is clear? So this is one method estimate, this is another, this is 1611 is a qPCR. And you can see that there is a good correlation between these 3 different methods. And each management decision based on that, the post or not to post, this was done last year, so this is the lowest number here, one of 4 units, I believe. And so the beach management decision based on these 3 methods, based on the 1600 is MEI, and this enterolab, and this is 000. I think this will be the new method, sorry. This will be the qPCR method. So the qPCR method, this will be 1611. I read the tables and I should have qPCR 1611 here. So the agreement is pretty good between all these methods. And what is interesting is actually from all, if you take just the coastal samples, now forget about the Maitai samples, Alamana stream samples. If you look here, we see that actually from all these 140 samples that we collected around the coast, 4% tested positive, were exceeding this value, which is very similar to that was actually reported on site earlier. So there was good agreement. It looks that we saw the same thing that TOH saw, the TOH sees in their samples. But what I want to get now is the inhibition, and I need to explain how inhibition works. So here's the qPCR graph. And I'm sorry if I'm talking you down and if you have seen qPCR a lot of times. So more DNA, more bacteria you have, earlier you are going to detect the signal. Less bacteria, less DNA you have, later you're going to detect the signal. So what we did was we took the DNA samples and we spiked each sample with external DNA, similar amount of external DNA. So this is actually a bunch of samples that got the same amount of DNA into each of them. And they should all come at the same time, to amplify at the same time. So it's, and the control is just a pool water. But what happens with your inhibition of samples, some of the samples are going to be delayed. So instead of getting the proper correct number, you're going to estimate that you have 3 units is roughly $1 reduction. So here is like $1,000 less, and some samples don't amplify at all. So if you don't count for inhibition of samples, it's really bad. So this is typical what we see in coastal samples. So this is for Hawaii coastal samples using the rapid DNA extraction methodologies. This is the water, and these are the samples. So what happens is when you do the EPA rapid extraction protocol, which is really nice because it's simple, you have all the DNA that you have originally in the sample, it all stays there. It's very quantitative. But unfortunately, there's something in Hawaii coastal waters that inhibits the reaction. So here are the data. So these are the 12 beaches. And here is how much we have this number of samples we have from each species. We have 13 samples, but I lost 2 of them because I was still learning. So 11 samples from each, and this is how many samples were inhibited and could not be evaluated. So, but what is interesting, when you collect the samples from the freshwater, you do not have this inhibition in the samples, and I don't know why. We think we have some ideas, but we still don't know why we don't have. If you go to the freshwater samples, it's very clear. EPA recommends to do 1 to 10 dilution of the samples when you see inhibition. So we took the samples and did dilutions, and as you can see, we didn't see much improvement. So you can't dilute it, keep diluting it, because if you dilute out your samples, so nothing is going to be left. So we have massive inhibition in our coastal samples. So a total of 69% of coastal samples that analyzed were inhibited and could not analyze. So that's why I need for comparison, I need to take the freshwater samples just to do the quantification. Dilution is not useful. And additional, what is interesting, we collected another set of filters for MS3D, so we don't have microbial source tracking. So we thought that when we have high concentration of bacteria, we can use MST tools to say where it's coming from. And when we took these filters and analyzed using the mobile soil kit, we didn't see any inhibition. It was all clean. I checked yesterday all the papers, and none of the samples had more than 1 PCR cycle inhibition. So they were all good. And so while I think the rapid methods are very useful, in the current form, I don't think that we can use them in Hawaii, so that's something that needs to be improved. So this is showing this one, the coastal water, and this is how looks the stream waters and the commercial kit. We don't see this thing. So I don't know what is. What we think what's happening is that we have coral sand, and we think that there's a coral suspension coming in the water. And when you use this rapid peak feeding protocol, you get the corals breaking down, and probably calcium that's in the water. Calcium is known to be an inhibitor of the QPC reaction. So that we think that the peak feeding and the calcium that stays in the water, in the column, because it doesn't precipitate in the spins, I think that might be the problem. But I don't really know. So that is something that we want to figure out what's happening. So now I'm going to talk about stuff that I know a little bit better. That's the microbial source tracking. So this is a way to tell where is the contamination coming from. So current indicator bacteria, if you look on E. coli and Enterococcus, are not source specific. Current indicator bacteria can grow in the environment and remain viable for long periods of time. So this is interesting picture that I saw again from the pool. No, I didn't Google, I know this before. And I went to the report, and what it shows is over the timeline what's the major source of beach closures. And the raw sewage is here, the yellow one. The rain and stormwater, non-point source is here. Here we don't know at all what's happening, and here the information is not provided. So the water quality standards are based on the non-point source. So we know only what the human health risk is really here. We don't really know what's happening in this area, what's the risk to the people is. So microbial source tracking tools are the way to say where is the contamination coming from. So its idea is very simple, it's not rocket science, it's just that the bacteria in the gut of the animals and humans is different. And it's important because health risk differs, if it's from the human or is it from the cat or raccoon, it's different. It's important in making the right management decisions and mediating conflicts between stakeholders like shellfish farmers. And it's a key component of human rights studies. So using the cultivation techniques, we can look on the bacteria or polyphores, and they look all same. And we can't really tell where they come from. We can look with SCM and they still look the same. If you look with molecular methods, we start to see that they look different, that there is difference between them. So typical target organisms are Bacteroides, specific polyphages, different groups of viruses, Enterococcus, E. coli, and others. These are used to distinguish between the different sources. So strategy, usually when you do MST, you do the site survey, you walk the streams. Best thing is to do it with the local stakeholders who are involved, because they have the knowledge and to know what's really happening at the site. I refuse to do it blindly. Some people do. I think it's very important. It depends what your issue, what value are, and then what your issues are. You use weighted evidence, so it's not like it's always clear cut. It's multi-tiered approach. It's good to do it in tiers, so you will not waste your chemicals. You do it step by step. You start with wider markers. You can do more specific markers depending what you find. Single sample has little value. You should collect samples with dry and wet weather, because dry weather, that shows you probably when there is a constant sewage input, for example, in the system. Wet weather might help you to figure out if the contamination is coming from the failing septic fields. Single marker has little or no value. So usually you use at least 2. We have used only 2, but because it's just done. Important limitations of MST. That's important. That people have huge expectations for MST. It's that it can solve all your problems. No, it can't. One thing is that it cannot give you the percentage between different sources. I really don't think that it can be done with current techniques, because there are several reasons for that. And there is no environmental marker. Well, we can test for humans, we can test for rabbits, we can test for chickens, we can test for all of different stuff, and then say that we didn't find any of these, it must be environmental. So I think that's the only way right now to do it. But I don't think that anybody has a special marker that recognizes environmental enterology. So key concepts, important, before you start your MST, you need to know how good your markers are. So you need to study how sensitive they are and how specific they are. So specificity is pretty much the cross-reactivity of your marker. So how many samples it does not cross-react. Number of true negatives divided by number of samples that should not contain the target. It's rough measure because it depends how many samples you study. Let's say if you have how many animals you study, but it's indication. So you need to know what animals it cross-react. Another thing is sensitivity. You need to know how many animals carry that marker. So is it 60% or is it 70% humans that carry human marker? It's important. So we collect samples in Hawaii. So that's what we did. So we went to collect poop. And we collected humans, we collected sewage samples, we collected cat, rat, and goose. We could not get the pig. I think it was very important, but we didn't have pig samples. We don't have dogs. I wish we had. So this is the samples that we have validated so far, or looked on the specificity. Human polyomaviruses. We didn't find them in humans or human fecal samples because they were collected very carefully. Stop it here. But it's not surprising because it's shared in urine. It's infection in kidney tissues that usually is how it's transmitted to the environment. Bacteroides marker is shown in 80 humans and is already in sewage samples. So here are the concentrations for the marker. So in the sewage, the human polyomavirus is constantly present at quite high concentrations. And this is what the human Bacteroides that we saw in the sewage. If you look at the cross-reactive animals, for example, cats and mongoose, that can also input some little into the environment. Then furthermore, they input little and the concentrations are much less. So, okay. So concentration of heterologous and human fecal samples tested. So this is showing you again the human Bacteroides markers in the fecal samples. It's more elevated than compared to the human enterological markers, enterological human samples. There's more human Bacteroides in the pool than there is enterological. And wastewater treatment plants. We have a study, we have ongoing study where we have collected samples from 4 wastewater treatment plants. I discovered 2 days ago that I haven't analyzed all of them for human Bacteroides and human polyomaviruses, but we have analyzed 1. And here are the numbers for enterology, Citer fringans, human Bacteroides and human polyomaviruses in the raw wastewater in the after primary treatment and in the effluent in standard wastewater treatment. So there is decrease of enterology and prevalence. Apparently the decrease of human Bacteroides and polyomaviruses is much less. I can understand the viruses are not removed effectively. That's no surprise. But I don't really know right now why human Bacteroides is more resistant to treatment, at least based on this study. So we also did, and Roberto helped me a lot with this data to get this analyzed. We did look also marker decay. What we did is we collected samples from the Manoa beach, and we collected samples, Manoa beach, and we collected the water from the Manoa stream. And we filtered it and we removed all the local fauna, grazers, everything, and we seeded it with sewage. And we measured it, it was triplicates, and we kept everything in dark, just to get the background, what will happen to the markers if there is no other factors involved except the grazers that are present in the sewage. Like removing everything totally. And so what we saw was enterology was measured by cultivation and by molecular method. And what's really important is the P90, which is like one log reduction time. And so Clostridium perfringens, it really stayed out for all 40 days. There was very little decrease in the concentration. So it's a very conservative marker. But it's usually settled or it's loaded out from the system. Human Bacteroides and human polyomaviruses. So the only major point here is to show is that actually the molecular signal decays fast. It doesn't linger around. It disappears from the water pretty good. We have some data also for the markers, and we haven't yet finished analysis, but I think it looks promising right now. Did I say everything on this slide? The decay of coastal water is slower than compared to stream water. This is probably related to the bias on the setup, because if you think about fresh water, if you think about sewage, it's mostly standard sewage is brackish, but it's I think 6 parts per thousand. Something like that, and if you put this one, if you put the craters that into the fresh water, they probably do better than they do in the marine environment. So that's my explaining why there's this different decay. Anyway, now let's move to actually something important. So now we have validated actually, I have some understanding how good our markers are. We know that there's some cross-reactivity with one of the markers, but it's not very high. We know that they're always present in sewage. Now we can move actually and start to do the MST on the watershed. So what I'm going to show is 1 year of data on the Manoa stream and Manoa watershed. So we have 9 sites, and we went every month, 1 month and twice, so we have 13 samples, and we collected samples above Mayan's Arboretum, half mile above that, and then downwards to the residential neighborhood and residential business-like neighborhood. And these are the enterology counts in the watershed, and these are the superfrequency counts in the watershed. And as we see, the tide is coming in, the error bars are getting bigger and the counts are getting smaller. So it's interesting that if you go to our right canal, it's actually cleaner than the stream itself based on enterology and superfrequency counts, because tide flushes in and out all the time. So these are the counts. These are the standards. So these are the threshold values. If anybody would consider Manoa stream a beach, but it's not. So here is the standard. So what's interesting is that if you go to this upper area in the rainforest, it would not be notified, because it's actually superfrequency counts are less than the limit. It will be notified in the stream, would be notified all the time, and I believe it's true for all the streams in the world. So superfrequency counts clearly shows that superfrequency supports actually the decision. What happens here is it's proof that these are actually exceeding the threshold level. And we look on the markers now on the same slide. So this is the human Bacteroides, human polyomaviruses. They're coming in immediately when they enter the residential area. this is really, there was two samples that were positive. One was below quantification limits and one was quantifiable. I'm not sure what's the source of it. Is it pigs? Is it some kind of not any cross-reaction with animals? I don't know. But it's clear that when we enter residential area, we see some kind of impairment in the system. But there is no news. We will, every time we see any development, we see some sort of impairment in the system. So how many percent of samples are positive for markers? So this one shows here.